Excellent. So I'd like to welcome you all to this ACAL seminar. It's my great pleasure to introduce Robert Tomasulo today. Robert began his career at IBM in 1956 and spent about 10 years in a variety of roles at IBM, and then moved on into mainframe development. And one of the key things that he did while at IBM is work on the Model 91. The floating point unit of the IBM Model 91 was the very first out-of-order execution functional unit in any computer system. And so Bob was the chief architect of the out-of-order functionality that really forms the basis of all of what we now have in our high-performance processors today. Following 25 years at IBM, Bob went on to work as a consultant for Amdahl Computing and in a variety of startups. And in 1997, he was awarded the ACM Eckert and Mauchly Award, and I'll read the citation for you here, for the ingenious Tomasulo's algorithm, which enabled out-of-order execution processors to be implemented. So please join me in welcoming Bob to tell us a little bit about his career today. Here you go. Let me slip that into your pocket.
We'll just put this right on here. Yeah. See if that works. Can everyone hear me, I should say? I can hear. Thank you very much for that kind welcome. What I intend to do with my time today is to divide it into two pieces, not necessarily equal. The first piece will be a very cursory examination of 20, 30 years of computer design from the Model 91 on forward to when it finally got displaced as an out-of-order execution machine. And then I'll spend the rest of the time answering your questions. By the way, interrupt me anytime that you have a question or a comment that you think is appropriate. So, to jump way ahead to like roughly 1990 or thereabouts, IBM finally brought out an out-of-order execution machine. And this was such a shocking thing that they felt it necessary to offer an explanation or two as to why it took them 30 years to do this. And they did, and the main explanation, which was quite a good one, was that once you have a cache with a very rapid access to memory, not counting misses, of course, which we can discuss a little bit later, then you don't have to worry about floating points, so you don't care about long execution instructions like floating point, then there is really no need for what the Model 91 offered. And so, naturally, they got rid of it. But as time marched on, it became apparent that they were going to need something. Now, IBM moves in mysterious ways. They probably were much slower than perhaps I would have liked or other people would have liked, but ultimately they get it done. So they brought out this machine, and as I said, they provided a reasonable rationale, which the only flaw in it, if you will, is that as time went on, because remember we're talking about like a 30-year span, it became less and less applicable to think that way, because memories kept getting slower, as they always have. I mean, you can think of it as kind of a golden age of the cache, that we had this period where you could get away with, 2-cycle access to main memory, and if you missed the main memory, you had like 5-cycle access to whatever backed it up, instead of, in today's machine, you got like 70-cycle access to whatever whatever backed it up. So after, let me get what I want to say straight, because I'm going to jump around somewhat. So with all these caveats, we didn't do an out-of-order machine. And maybe we could have a little bit sooner than otherwise. Now we jump back to the Model 91 time frame. And why didn't they do an out-of-order execution machine then? Well, they did. They did. It was a machine. I forgot what the nomenclature was now, but it was a full out-of-order machine. It was completely logically designed. It wasn't physically designed. So it's hard facts, and it featured some very nice innovations, including a branch prediction table, which was a relatively new thing, and what else did they have? Oh yes, they had something in there, especially for RAS purposes, which may slip my mind. No one cares about RAS anyway, although we should. So this machine was carried through to everything except final physical design. So it's as good as gold. I mean, it was completely debugged and conformed to the architecture and all that other good stuff. And it was deemed that it was too expensive, which it probably was. By the way, it had like a 7 nanosecond cycle, which for this period of time was pretty good. Pretty good. Contemporary IBM machines were like 40, 50 nanosecond cycles at that time. So now we sort of have nothing because we excuse me, we don't have the Model 91 anymore, and we didn't bring out a successor machine. So, in a sense, nothing happened from that point of view of machine design for 30 some odd years, which was sad, I think, but that's okay. Does anyone have any questions? Here, yes, I don't have questions. I just leapfrog to the rest of my talk.
There you go.
Or rather the rest of your talk, because I didn't have to do too much talking. As you can see, I don't have much to do because IBM made it too easy, right? They made one, I wouldn't say it was a half-hearted attempt. They made a good attempt to make a really good machine, but it wasn't in the cards, and that was it. Okay? 30 years go by, and then it's in the stars, and they can start over again. So that's really what I sort of the main thing I wanted to cover. I can cover more things if you want. I mean, obviously, machine design didn't stand still during this period. There were improvements in RAS and all kinds of things. But for our purposes, I didn't think I would want to devote too much time to those things. So does anyone think we ought to spend some time on some aspects of...
Question over here.
Yeah.
What was the date on that machine?
I'm sorry, which machine?
The one, the complete out-of-order machine.
The Model 91 that we actually built, or...
The one that you didn't build.
Oh, that we didn't build. My memory isn't that good. It was around the early 70s, 72.
Did that have more than one instruction at the time to decode?
Yes, in in a limited way. Basically, what it did was to classify the instructions into fixed point, floating point, and decimal. And one instruction in each class could be executed along with an instruction from another class. So it didn't rely really heavily on out of order, because you have to remember that it is still true that with the cache, a lot of the gain of out of order evaporates. So there's not much point pursuing it just for the sake of pursuing it. Anyone else? No. Oh, yes, good.
How large would a team of people, like for the processors that you described, how many people would work on one of those projects?
How many people?
Yeah, like right now Intel would have thousands.
Well, yeah. The Model 91 was special in the sense that they did a whole new technology. They did a whole new design automation system, and they did a whole new machine. So they had a lot of change on their plates. And you want to explore that some more?
Well, yeah. So, how large would those teams be then? Like, how many people?
Oh, how many people? Yeah. Well, the Model 91, because it was developing the design automation system and the software and everything, had a lot of people altogether. It didn't have that many if you focus in on the designers, people like I was. There might have been, 3, 4 groups, 20, maybe, order of magnitude. Why is order of magnitude funny? You think I'm trying to hide 100? No, I wouldn't do that. Good, if you want.
So, what was the most difficult part that you found when you were trying to do the Model 91 design? Like, what gave you guys the most trouble, do you think?
What gave us the most trouble in the real 91? Well, of course, initially we had trouble till we discovered the out of order algorithm, so that cleared up one source of trouble. The whole machine was stretching. It was a strange machine because it had really pitiful memory access. This was before caches, so it had like 10 cycle minimum memory access. Now, of course, it had 16-way interleave memory, right? So you're not necessarily waiting 10 cycles for every single access, but it's pretty pitiful. So memory was a big bottleneck for that machine. When they finally, I think they brought out one, as part of the 90 line. I may be misremembering it, but they may have brought out a high-speed version. I seem to remember they made 2 versions of a thin film memory machine, which was very fast memory. Unfortunately, it couldn't have the huge number of megabytes that you can get in more conventional memories. Anything else?
I'm going to take the pause.
Pardon?
Your mic jumped off.
Oh, keeps jumping off. Well, it's my...
Maybe
Here,
you want to
maybe...
hold it?
No, I think let me get this out of my pocket. Okay, now where can I put this?
You can just pop that right back in there.
Be safe.
So, I have one question
Sure.
for you. Let's see if this thing will work. If I stick it over here, let's try.
Yeah, you should have plenty of room.
If I can get the clip to work. All right. So earlier today...
You can hear? Everyone can hear? Okay.
So earlier today we were talking about what you did after IBM, and then you went on to work at STC, I believe you said it was, and worked on one of the first microprocessor-based kind of mainframe.
Yeah.
So can you tell us a little bit about what are the features that were coming out of this history at IBM that would make this server machine different from the other PCs that you had at the start of the 80s there?
Yeah, there's a couple of parts to that question. As is often the case with a big company like IBM, they're not necessarily first out of the gate with new things. It may take them a while, especially if they don't have competition. So part of what happened is due to that kind of phenomenon. But I don't know that the rest is due to that. Say a little more about what you have in mind.
What were the specific kinds of design features that you were trying to make your machine in 80 different from the PCs that everyone else was
Okay. You have to understand this machine that we did, the first one we did as STC, the only one we did as STC Corporation, was not supposed to be a high-performance machine. Right? It was supposed to be below the IBM machines because it was supposed to serve as a kind of a server or however you want to look at it, a lead-in to the IBM machine. Now, reality kind of intruded, and the first thing that happened, the technology was like 2 times slower than we thought it was. But fortunately, it was also 2 times faster than we thought it was. So we recouped that. And then we were still in the hole, and we had to end up pulling some pretty sophisticated tricks. And you don't want to do that. You're dealing with a group, not all, but a group of neophytes, and you don't want to be tackling complicated things if you can possibly avoid it. So that sort of partially was what did them in. Right? It was too complicated for them.
So that was a marketing failure of the STC.
Yeah, and God love marketing people. I wanted to strangle them. We were going, for 3 years on this project, sweating bullets to try and wring out every last bit of performance that these guys, the marketing people, were telling us, you absolutely need that performance because we're going to put you in a certain environment where if you don't have it, we're not going to be able to sell a lot of machines. And then what happens? They said, oh no, we don't really have to be in that environment. We want a cheaper machine that doesn't go as fast. Coke. I wanted to strangle them, all of them. So it happens, right? It happens. Anything else? By the way, this is not the end of the program. You can think of it as the beginning of the second part of the program where you get to ask questions. So either way you want to look at it. Go ahead.
So how did you find that for moving from IBM on the System 360 stuff through your consulting into STC, how did, over those years, did you find that your job as a computer architect changed?
Oddly enough, I don't think that much. As I said, and it was a mistake, striving for too much performance was bad. Okay, we got ourselves a lot of grief from doing that. Because, the architecture of the machine is semi-stable, right? It changes. You have to upgrade with the times, but it's I'd say semi-stable. So, well, anyway, okay, go ahead. How about some people in the back there? Are you getting paid to take this course? Or?
Did I see a hand in the middle over here? Or was I
Yeah. Middle is good.
Go ahead.
So, what was the original motivation for trying to do the out of order architecture? Because it seems like it was sort of an idea that was ahead of its time. It was 20 years or so before it was actually produced. What was the original motivation for it?
Well, I lost part of the end. I know you were asking for the original motivation for doing out of order. Mm-hmm. Were you asking like another part that I should know about?
Sort of like how come it took that long to be used in production? Was too expensive?
How can what? I didn't hear you.
How come it took so long for it to be used in production?
Oh, in production.
And why was the idea ahead of its time?
Yeah. Well, the short answer to that was we've already discussed it. One, there was a machine successor that got scrapped. Without that machine and with the advances in the cache, there was no point really in out of order execution, at least not until the 80s. You can argue about at what point it might have made sense. So does that?
So given that, why did you try to do out of order at all? Why didn't the get together and decide to go after?
Yeah. At the time, we were young, young and bold, and we wanted to go for everything, right? That we could get, right? And we had if we hadn't had the idea, we would have built a perfectly good machine, which in the best case, it might be 20 or 30% faster, thanks to my friend, the floating point guy, because he speeded up the original floating point. So it wasn't that big a deal, right? But it certainly was how should I put it? It was a coup, right? It was something that Seymour Cray didn't have. Nobody had it. So IBM could get some bragging rights out of the whole thing. But come on, it's a big room. Yes, ma'am.
So back to late 60s and early 70s, how was it to convince the fellow designers about the idea of out-of-order code?
I'm sorry, I didn't catch the last part.
How was it like to convince your fellow designers and architects about the idea of an out-of-order processor?
Oh, how is it for me to communicate?
Yeah, how did you convince your team this was a good idea?
Oh, the team. They're a pretty smart team. didn't take any convincing. I had the idea on a weekend. I went in Monday morning, sketched out, the bulk of the important parts of the idea, and with very few, they were thorough, right? So they made sure they covered things, but there were really no serious quibbles, and we were off and running. Now, that you can do more with out-of-order execution than we did. Okay? In particular, one thing you can do, which is very, very important for the operating system, is to be able to do loads out of order. Okay? So that you can stack up loads that might be delayed for whatever reason, and maybe get some other instruction through. Because that's the main. Once you get rid of floating point, for which I say long instructions. Okay, once you get rid of long instructions, then that's basically it, right? And so even the out of order that I was just talking about is not, really a barn burner kind of thing. it's good to have. And as with all these things, you get to build on them. Right? We didn't get to build on them for 30 years, but you get to build on them. And out of the closet they come, and you find that now you can do something you couldn't do before. Yes?
What kind of design automation did you have to work with on the Model 9?
None. we were the first machine in IBM to simulate the logic of a machine, and we could simulate 1,000 gates at a time, which is pitiful. I mean, the Model 91 isn't by any means a huge machine, but it's like 40 or 50,000 gates, so that's nothing. And we didn't. This was something that developed toward the end of the project. Like I said, we had, I got to give loads of credit, we had a lot of smart people. I mean, including this one guy and gal who were really DA people, and they were pushing, what they could do to improve the performance of the machine. So
Bob, earlier today we were talking a little bit about the debugging efforts and the kinds of problems that you had in these early machines. Can you tell us a little bit about the kinds of bugs and what was the process that you as a team had to go through to fix them?
Yes. An interesting sidelight of that is that we had this programmer who eventually wrote a simulation of the machine. And he discovered 2 bugs in the machine having to do with, I think it had to do with fetching stuff. Because we had, for those days, we had a pretty sophisticated fetching algorithm where you start out with nothing and then you try and catch a loop. Excuse me. So we really didn't have very much of anything in the way of debugging. It was coming, but not for us, which is too bad. And did I see a questioning look back there? No?
So let me follow up on my previous question.
Sure.
So on the hardware side, you get this machine, you build it, I assume you hit the switch, it doesn't work.
Yeah.
So, how would you get from the first time you flip the switch to a machine that would do what you want?
Excuse me a minute. So you're really asking how do you debug the machine? Is that what you're asking? Well, that's somewhat of an art, especially in those days. Now, we had an interesting experience. We were plagued by a little something called the crack stripe, which none of you probably ever heard of. But it was a fault in the technology due to the extremely high current density that they had pushed the circuits to, such that you can think of it, the electron wind going through these very fine circuits were blowing the atoms away, and you would get faults. You would get open circuits in things that. So that was an interesting problem that we had to deal with. Did I leave out something?
So how do you go about figuring out a problem with that? How did you find that this was going on? Right? You try on the machine, it doesn't work. But now you know it's this crack stripe.
Yeah, the crack stripe is special. We were experiencing one failure every day. Now, I don't know, most of you don't have any experience debugging a machine, but you can't debug a big complex machine if you have one failure that you got to find every single day. right? There are just too many things to find. So we were in real trouble, and the answer was technology. Ultimately, they had to fix the technology, and in the case of 91, they remade all the technology. In the case of some of the slower machines in the 360 line, they only partially remade them, and some they didn't remake at all, because it was a time-dependent thing. Right? The faster your circuit was, the more it was prone to this problem. Yes?
So how long, on average, were these systems under development? Like from Thomas Watson saying, I want a fast computer, to them saying, here you go.
What I have to do, unfortunately, which doesn't make a nice, clean picture, is the following. We commenced on the Model 91 in about 1963, possibly late 62. I don't remember. And because of the cracked stripe problem, it took us a very long time to finally debug the machine. If there had been no cracked stripe problem, we probably would have brought up the machine two years earlier than we ultimately brought it up. So that was a real devastating blow to us. And it's really hard. When your hardware is failing underneath you, it's hard to make progress, and it's failing in random ways. And sometimes you take it out of the machine and it doesn't fail. Now what do you do? Well, thank your lucky stars. So it fails the next time. Yes, sir.
So in the course of the process of developing the Model 91, was there ever a point where you thought about compiler optimizations that could make programs run even faster on it, or was that sort of totally out of the picture?
I'm sorry, what kind of optimization?
Compiler optimization.
Compiler optimization. Well, we didn't have much to say about compilers. I mean, I was in the hardware group. Now we were conversant with some of their problems, and later on it was more back and forth, because I always had, after the initial Model 91 thing, I always had a dual role of architect in the early phases, which is really software architecture, and then implementing the machine. So that answer your question?
Yeah, I guess.
Oh, excuse me. Any more?
Yeah.
Yeah.
You mentioned Seymour Cray a minute ago, and I think Cray was still at Control Data at the time.
Yeah, I believe so. Yes.
Was there a lot of competition there? Did you go out and buy the latest Control Data machine every week and take it apart and see how it worked?
Yeah. No. We did a little more of that later on, but we didn't do that that much. He had, again, very, very interesting the way these things work out. He had a jump start on us, okay, because he was already working on his machine, and we were just starting on. All right, we didn't even have the technology to build our machine out of, right? So we were in real trouble. So, what are we to do in this circumstance? How are we to make up lost ground, so to speak? So, we tried, all kinds of things, some perhaps not well founded, to try and make up this lost ground. But it's difficult, and what happened was, we were saved. What happened was, we had an assessment of how fast the Cray machine was. And we said, okay, we think it's this fast. They're going to be 2 years after us So we got to be twice as fast as them so that we can, come out. Okay, fine. That sounds reasonable. Well, it turns out that the Cray machine is 4 times faster. The new machine is 4 times faster than we thought. But meanwhile, our machine turns out to be 2 times faster than we thought it was. So the net result of all this fiddling around was rough parity. There were some kinds of problems we did faster. There were some kinds of problems they did faster. But I think they still had, perhaps undeserved, the reputation for, raw compute speed. And I think all of the customers, like the Atomic Energy Commission, laboratories that were supposedly interested in that, they all went to Cray. And IBM sold to, how do I want to characterize it? Database kind of applications that need a lot of memory and concurrency, a lot of I/O running and all that kind of stuff. Not particularly, doesn't need floating point performance or computational performance in general. Well,
so Bob, can you tell us a little bit about, you were at IBM for a long time.
Yep.
Can you tell us about how the culture of IBM as a company changed over the course of your career? Do you have any thoughts?
See, that's a tough one from the inside. Well, first of all, I got to divide my career into 2 parts. My 5 or 6 years when I did not machine design related stuff, and then after that, okay. So, excuse me. I lost my thread. Give me.
It's how did IBM change over the course of your career?
How did IBM change?
As a company.
Oh, as a company, yes. It became less interested in cutting edge, for one thing, right? It was, like I said, in the beginning, it was wide open. Crazy ideas, if you could implement them and it would buy some performance, you got it. As time went on, you get more and more constrained by the architecture and by the necessity of other machines, right? You're not allowed to design just for the Model 91 class. You have to design a machine for the next class down and the next. They had 3 or 4 by that time classes. So there are all kinds of things standing in the way of pure performance, and you just have to live with those because there's no way around it.
How much did backward compatibility, binary compatibility, play into?
Oh yeah, we had it. That was a must. That was a no-brainer. We weren't allowed to touch that with a 10-foot fall. In fact, we had to get a special dispensation because the Model 91, because of its out-of-order floating point effect on interrupts, was actually in violation of the architecture. And they had to get a special dispensation for the Model 91. I don't think anyone ever suffered from this dispensation in those days, but nonetheless, you had to get it.
So were there any specific ideas that teams you worked on came up with that ended up dying or required changes?
Let me see if I understand. You're asking me if there were ideas that sort of died.
Well, yeah, like any ideas that you guys thought were really, really good that just wouldn't have worked because of things like
Excuse me. These cough drops are getting ineffective. That's really hard to answer. You like to think that you wring out, the most performance that you can get out of your technology and what you've got, but that isn't really true. There are all manner of compromises that have to be made. Some have to be made, others don't have to be made, but you're not omniscient. You don't know everything. So that it's really hard to say how much that affects machine design.